This short presentation shows the results of a study carried out to evaluate the feasibility of a low-cost active reflector for deformation monitoring through Sentinel-1 images. All the authors are from the Centre Técnologic de Télécommunications de Catalunya. In space-borne interferometry, passive corner reflectors are often used as standard ground points when natural permanent scatters are not available, in areas incoherent, and when the radar scattering is temporally unstable. Radiometric calibration and phase stability can be checked using their responses. The use of passive corner reflector is not always suitable, especially in areas as glaciers, snow-covered regions, and mountain slopes, where due to a difficult accessibility, installing passive corner reflectors can be very time and cost consuming. Furthermore, severe weather conditions can jeopardize their performance. An alternative to passive corner reflectors can be represented by the installation of active reflectors, more compact and lighter. The main limitation of an active reflector is the need to have available a power source and the stability of its radio frequency chain over a long temporal interval. Basically, an active reflector is a device which, when the satellite passes overhead, receives the signal and retransmits it with higher strength using the energy of the power source. The device here described is the simplest transponder whose performances are different from those of systems specifically designed to provide the best absolute radiometric and phasemetric calibration. In the last decade, a few of active reflectors have been made available from the market for field campaigns, but till now their use does not yet spread. Their performance should allow through DINSAR to measure vertical displacement of 1 mm. The proposed active reflector is designed to provide a fair performance cost-benefit and a low power consumption, to make feasible the setup of a dense network of active reflectors, also with an accuracy in the order of 2 mm. To provide an adequate signature and the required phase accuracy for Sentinel-1 based DINSAR, the radar cross-section of the target must be greater than 40.4 dB square meters. Just to give an example, this is the radar cross-section of the triangular triaedral whose size is 1.7 meters. There is a simple formula to calculate the radar cross-section of an active reflector. Consider the gain of design and implemented antenna is 17.4 dB. We can estimate the gain required for the amplifying section, about 42 dB. The stability of its amplitude and phase response is basically affected by the presence of active radio frequency components susceptible to temperature changes. When the active reflectors are installed for a large period, from months to years long, the natural variation of the air temperature demands a careful thermal control of the device. Here you can see a picture of the system and the setup used to test the sensitivity to temperature variation of the amplifying section and the variation of a virtual displacement introduced by the device in laboratory. Also, the pulse shape after the transmission has been checked. The test signal was generated using a vectoral network analyzer to simulate the Sentinel-1 signal. A data acquisition was carried out at close range to estimate the relationship between the phase response of the active reflector and the temperature variation. This curve will be used to correct a posteriori the acquired phase data. An active reflector is installed together with a passive corner reflector since October 2019 in the UPC campus, where CTTC is located, on a very stable concrete basement. The response can be checked at every Sentinel-1 passage, using for example a Sentinel-1 app browser. Using the DINSAR processing, the measured phases versus the acquisition date can be plotted. A significant instability can be observed. After correcting the data using the calibration function, the error reduces, maintaining the fluctuation between plus and minus 2 mm. Another test was carried out in Slovenia, where the active reflector was installed together with the GPS station. Also in this case, using the correction curve, the phase instability is limited to a few millimeters. In conclusion, applying the calibration curve, the response of the active reflector complies with the design requirement. By the way, the main issue for a stable response is confirmed to be the temperature, which is in the present version is not controlled. Despite the different setup and experimental condition, the behavior of the active reflectors appears to be highly repeatable. The actual correction is carried out offline, but the last active reflector prototype now includes an internal temperature sensor and the built-in hardware and software tool for a real-time correction can be evaluated, taking care to not increase too much costs and power consumption. Thank you for your attention.